All right, welcome. Today, we're going to build a bridge between two pretty different worlds, the visual, intuitive world of geometry and the super precise, powerful world of algebra. We're going to get right into the foundations of conic sections by doing a deep dive on the first and, let's be honest, most perfect one, the circle. Okay, let's jump in. So, let's start with a really big question. Think about it. You can draw a shape, right? Any shape. Like a circle. You can see it, you can sketch it, but how do you capture its perfect essence in the language of math? How do you turn that drawing into an exact, undeniable equation? Well, the answer is surprisingly simple, and it literally changed math forever. You do it by giving every single point an address, a unique location. This huge idea is called coordinate geometry, and that's the secret code we're about to crack today. All right, let's crack this code. It all starts with the map, right? The framework we use to give every single point its unique address. Now, what I love about this is how it connects a super simple idea with the formal one. On the left, you've got the fifth grade explanation we all remember, just plain old graph paper. An address like 3, 2, that just means 3 steps to the right, 2 steps up. So easy. Then on the right, we've got the formal language. It's the Cartesian plane, with a horizontal x-axis and a vertical y-axis. But here's the thing. The core idea is exactly the same. Every point gets its own unique x, y coordinate. Okay, so we've got addresses for every point. Cool. What's next? Well, if you have 2 points, 2 addresses, you gotta have a way to measure the distance between them, right? We need, a universal ruler that works anywhere on our map. And you know what? The intuition here comes from something we all learned back in school. If you want the straight line distance between any 2 points, you can always just imagine a right-angled triangle connecting them, where that distance you want is the hypotenuse. From there, it's just good old Pythagoras' theorem. A squared plus b squared equals c squared. You know it. And this is where it all clicks. This shows you exactly how that geometric idea gets translated into algebra. The distance formula you see here? It is literally just Pythagoras' theorem, but written in the language of coordinates. The change in x, that's one side of the triangle. The change in y, that's the other side. This formula, man, it's the foundational tool that powers everything we're about to do. All right, so we've got our toolkit, we can give points addresses, and we have a ruler to measure the distance. So let's use them. Let's build our first and, most perfect conic section, the circle. So what is a circle, really? This simple analogy just nails it. Imagine a school is your center point. A circle is just all the houses that are exactly 2 kilometers away from that school. Not a bit more, not a bit less. Simple, right? And there it is, the formal definition. But listen closely, and you'll hear the school and houses in there. A circle is simply the set of all points that are the same distance, that's the radius, from one single fixed point, the center. It's the exact same idea, just in math speak. Okay. Now for the magic. Let's see how this definition plus our universal ruler gives us the circle's equation. Step 1. We just say what we mean. The distance from the center, let's call it h, k, to any point on the circle, x, y, is always the radius r. Easy enough. Step 2. Now we just translate that sentence into math using our distance formula. See? Step 3. To clean it up, we just square both sides, get rid of that pesky square root. And step 4, bam, that's it. That's the equation. This is the standard form of a circle, and it comes right out of the definition. It's so elegant. Okay, that standard form is awesome. It's clean. But, out in the wild, in your homework, on an exam, you'll often see the circle's equation wearing a disguise. You've got to be able to recognize both of its faces. So on the left, we've got that standard form we just figured out. Its superpower is that you can just look at it, and boom, you see the center, hk, and the radius r. Instant. But on the right, we have the general form. This is what you get if you multiply out all the brackets in the standard form. It looks way more complicated, and honestly, its main purpose is that this is how problems are usually thrown at you. So how do we decode this thing? This slide is your Rosetta Stone. If you get an equation that looks like this general form, you can pull the center and radius right out of it. The center is just -g, -f, and the radius is the square root of g squared plus f squared minus c. This lets you cut right through the mess and find what you need. All right, let's put it to the test with a practice problem. The kind of thing you'd see in a math competition. You're given this equation in general form. Now, you could use the formulas from the last slide, but there's an even more powerful technique called completing the square. What that really is, it's an algebraic move for taking all those jumbled up x and y terms and wrestling them back into those nice, neat brackets we saw in the standard form. This is a skill you absolutely have to master. Okay, we've gone from a simple idea of addresses all the way to deriving and decoding these complex equations. So, what's the payoff? Why does mastering this stuff actually matter? Well, this slide really shows how each tool we've talked about builds on the last. That distance formula, that's the bridge. The circle equations, that's what you use to solve all kinds of problems about paths of points or tangent lines. Completing the square is just a powerhouse technique in all sorts of advanced algebra. And all of this is the bedrock for understanding the other conic sections, which are totally essential in things like physics and calculus. Okay, before we wrap up, let's talk about some common traps to avoid. First, watch your signs. When you pull the center from the general form, remember it's -g, -f, not gf. Super common mistake. Second, when you're completing the square, you have to do it for the x terms and the y terms. Don't forget one. And finally, and this is a big one, not every equation with an x squared and a y squared is a circle. The numbers in front of them have to be the same, and you can't have any xy terms floating around. And that brings us to our final, and maybe most powerful, piece of advice. The real strategy here, especially when problems get tough, isn't just to mindlessly plug things into formulas. It's to always remember the geometry hiding behind the algebra. Always ask yourself, what does this equation look like? What does it mean as a shape? Using that geometric intuition to guide your algebraic attack, well, that's the real key to becoming a brilliant problem solver. So, what shape are you going to decode next?